Deep learning is a subfield of machine learning that deals with training artificial neural networks to perform complex tasks such as image recognition, natural language processing, and anomaly detection. It is a powerful tool that enables computers to learn from data and improve their performance over time without human intervention. The concept of deep learning originates from the idea of artificial neural networks, which are modeled after the structure and function of biological neurons in the brain. These networks consist of layers of interconnected nodes or neurons that process data inputs and produce outputs. The deep learning approach differs from traditional machine learning in that it can handle large amounts of data and learn more complex relationships between features without being explicitly programmed. This is achieved by training the network on a vast amount of data through an iterative process called backpropagation. One of the main advantages of deep learning is its ability to extract meaningful features automatically from raw data, making it suitable for tasks such as image recognition or speech recognition. For example, a deep neural network can be trained to recognize different objects in an image by analyzing various features such as edges, shapes, textures, and colors. Another important concept in deep learning is convolutional neural networks, CNNs, which are designed specifically for visual recognition tasks. A CNN consists of several layers that perform feature extraction, convolution, pooling, and classification. The feature extraction layer extracts the most relevant features from the input images using filters or kernels. The convolution layer applies these filters to the input images to detect patterns or edges at different scales. The pooling layer reduces the size of feature maps by downscaling them to preserve only the essential information. Finally, the classification layer uses these features to classify each input image into one or more categories based on learned weights and biases. Recurrent neural networks, RNNs, are another type of deep learning architecture commonly used for natural language processing tasks such as speech recognition or language translation. Unlike CNNs, RNNs can handle sequential data by processing information in a repeated loop and storing the previous state. This allows RNNs to capture long-term dependencies in the input data, making them more suitable for tasks that involve context or temporal features. For example, an RNN can be trained to generate a sequence of words based on a given input sentence by predicting the most likely next word at each step. The training process for deep learning involves optimizing the network's parameters or weights to minimize the error between predicted outputs and actual outputs. This is achieved by using backpropagation to calculate the gradient of the loss function with respect to each weight and adjust them accordingly. The most commonly used optimization algorithm in deep learning is stochastic gradient descent, SGD, which updates the weights based on a small subset of training examples called mini-batches. Other optimization techniques such as ADAM or AdaGrad can also be used to improve training speed and accuracy. To avoid overfitting, which occurs when the neural network becomes too specialized to the training data and fails to generalize well on unseen data, regularization techniques such as dropout or early stopping can be applied. These methods prevent overfitting by reducing model complexity or stopping training early when validation error stops improving. In conclusion, deep learning is a powerful subfield of machine learning that enables computers to learn from data and perform complex tasks such as image recognition, natural language processing, and anomaly detection. It relies on artificial neural networks that are trained through backpropagation and optimized using stochastic gradient descent. Concepts such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs, have been developed specifically for visual recognition tasks and natural language processing tasks respectively. With its ability to extract meaningful features automatically from raw data, deep learning has vast potential for various applications in fields such as healthcare, finance, robotics, computer vision, speech recognition, and more. Deep learning is a type of artificial intelligence that allows machines to mimic the way humans learn and process information. In simple terms, it is a method of training a computer to recognize patterns in data so that it can perform tasks with greater speed and accuracy. Traditional machine learning algorithms are built on a set of predefined rules that are used to classify data. With deep learning, however, the computer is able to learn directly from the data without being explicitly programmed. This means that it can identify features and patterns in the data that might not have been evident to humans. Deep learning algorithms are built using artificial neural networks, which consist of multiple layers of interconnected nodes or neurons. Each neuron takes input from other neurons and applies a mathematical function to produce an output. By adjusting the strength of the connections between neurons, the network can learn to recognize patterns in data. One example of deep learning in action is image recognition. A deep learning algorithm can be trained on a large dataset of images, such as photographs of cats and dogs. As it processes each image, it learns to identify distinguishing features such as fur texture or ear shape that differentiate cats from dogs. Once trained, the algorithm can accurately classify new images as either cats or dogs based on these learned features. Deep learning has many practical applications across a wide range of industries. It is used in speech recognition software, self-driving cars, medical imaging analysis, and even financial fraud detection. To develop a deep learning algorithm, there are several steps involved. 1. Choose your data. The first step in building any machine learning model is selecting an appropriate dataset for training and testing your algorithm. In deep learning projects, this might involve collecting large amounts of labeled data or using pre-existing datasets like ImageNet or NIST. 2. Pre-processing. Once you have your dataset ready, you will need to pre-process your data before feeding it into your neural network model. This might involve tasks such as resizing images, normalizing data, or handling missing values. 3. Building your model. The core of any deep learning project is building your neural network model. There are many types of models to choose from, including convolutional neural networks, CNNs, for image recognition and recurrent neural networks, RNNs, for natural language processing. 4. Training your model. Once you have built your model, you will need to train it using your pre-processed data. This involves feeding your data into the network and adjusting the strength of the connections between neurons to minimize the error between the predicted output and the actual output. 5. Testing your model. After training your model, you will want to evaluate its performance on a separate set of testing data that it has not seen before. This helps ensure that your algorithm is able to generalize and make accurate predictions on new data. 6. Deploying your model. Once you are satisfied with the performance of your deep learning algorithm, you can deploy it in a production environment where it can be used to make real-time predictions or automate tasks. While deep learning has many advantages in terms of accuracy and speed, there are also several challenges that must be addressed when developing these algorithms. 1. Data availability. Deep learning algorithms require large amounts of labeled training data in order to learn effectively. This can be a challenge for some applications where obtaining labeled data is difficult or expensive. 2. Overfitting. When training a deep learning algorithm, there is always a risk of overfitting, meaning that the algorithm becomes too specialized and performs poorly on new data. Regularization techniques such as dropout or weight decay can help prevent overfitting. Computing resources. Training deep learning models can require large amounts of computing resources such as powerful GPUs or specialized hardware like Google's Tensor Processing Units, TPUs. This can make it difficult for smaller organizations or individuals to develop and deploy their own deep learning algorithms. 4. Interpretability. Finally, one of the biggest challenges with deep learning is interpretability, meaning that it can be difficult to understand how the algorithm is making its predictions. This can be a concern in applications where there are legal or ethical implications for incorrect predictions. Despite these challenges, deep learning has become an increasingly important tool in the field of artificial intelligence. With its ability to recognize patterns and make accurate predictions, it has the potential to revolutionize many industries and improve our daily lives in countless ways. Welcome to this technical instruction video, where we will be discussing the difference between machine learning and deep learning. Machine learning and deep learning are two of the most popular buzzwords in the field of artificial intelligence. These terms are often used interchangeably, but they are not the same thing. In this video, we will explore what machine learning and deep learning are and how they differ from each other. Firstly, let's start with machine learning. Machine learning is a type of artificial intelligence that enables machines to learn from data without being explicitly programmed. In other words, machines can learn from past experiences and make predictions or decisions based on those experiences. This is achieved through the use of algorithms that analyze data, recognize patterns, and make decisions. Machine learning has several subcategories, including supervised learning, unsupervised learning, and reinforcement learning. Supervised learning involves training a model on a labeled dataset so that it can predict outcomes for new examples based on previous input-output pairs. Unsupervised learning involves training a model on an unlabeled dataset so that it can identify patterns or groupings in the data without any prior knowledge of what these patterns might look like. Reinforcement learning involves training an agent in an environment to maximize its reward by taking actions that lead to positive outcomes. On the other hand, deep learning is a subset of machine learning that focuses on algorithms known as neural networks. Neural networks are designed to mimic the structure and function of the human brain by using interconnected layers of artificial neurons to process information. Deep learning algorithms work by building multiple layers of interconnected neurons that process data from input to output layers using specific activation functions like sigmoid functions or ReLU functions. These neural networks use backpropagation algorithms to adjust the weights associated with each connection between neurons during training so they can adjust their predictions based on data inputs. Deep learning has become increasingly popular in recent years due to its ability to solve complex problems such as image recognition, speech recognition, natural language processing, and game playing. Deep learning algorithms are also used in autonomous vehicles to help them navigate through complex environments. So what is the difference between machine learning and deep learning? The main difference lies in the complexity of the tasks they can perform. Machine learning is a broad term that encompasses a variety of algorithms that can be trained to recognize patterns in data. Deep learning, on the other hand, is a subset of machine learning that uses neural networks to process data and learn from it. Deep learning takes machine learning to another level by introducing artificial neural networks with multiple layers that can learn from more complex data structures. This makes deep learning algorithms more complex but also more powerful than traditional machine learning algorithms. Deep learning has been used for many applications such as image recognition or natural language processing that require more sophisticated algorithms. Another significant difference between machine learning and deep learning is their level of data requirements. Machine learning requires less amount of data compared to deep learning methods. For example, a supervised algorithm in machine learning might require thousands or millions of labeled examples for training but only several hundred for unsupervised methods. Whereas deep learning methods need large amounts of labeled training examples to effectively learn from them. The third major difference between machine learning and deep learning is computational power requirements that differ significantly between both techniques. Deep learning requires much more computational power because it trains by running multiple layers simultaneously, so computations get expensive quickly. This means it may take weeks or months to train a large-scale neural network on modern hardware, whereas traditional machine learning methods can be trained on much smaller datasets using less powerful machines. In summary, both machine learning and deep learning are subsets of artificial intelligence that allow machines to learn from data without being explicitly programmed. However, the key difference lies in their complexity levels regarding the types of problems they can solve, the amount of data needed for training, and their computational power requirements.